So at this point, we've developed our model of the solar system. The heliocentric model is the model of choice. The Sun is at the center of the solar system, and all the planets go around the Sun in orbits. Now, at this point in the development of our model of the solar system, there are still a few problems. And we're going to talk here about planetary motion and Kepler's contribution to bringing physics into astronomy and solving the problem of planetary motion in the heliocentric system. Well, most of its problems. So we're going to talk through Kepler's laws. We're going to talk a little bit about Kepler, some things on ellipse geometry. So how does an ellipse look? How does it deviate from a perfect circle? And talk about some of the mathematics that apply to this. We'll then talk through Kepler's 3 laws and their development, and then look at their effects. So the story of Kepler really begins with Tycho here, or at least the story of Kepler's laws. Here is Tycho. Remember Tycho Brahe, this huge personality, the Danish astronomer royal. And here he is with the Danish king Rudolf II. And he's presenting to him here a number of astronomical discoveries and equipment. Here he is with a globe of the stars, an armillary sphere, charts of the stars in the sky, and of course over here sighting equipment for looking at the positions of stars in the sky. And this was really Tycho's big achievement. Tycho Brahe had amazing measurements, very, very accurate measurements of the positions of the stars, and very, very accurate measurements of the positions of the planets in the sky. And this is where Johann Kepler comes in. Kepler was a man who was interested in looking at the positions of the planets and attempting to quantify the orbits of the planets. That is, to figure out why the planets moved as they did in the sky and actually surmise what did their orbit look like. And so Kepler became essentially a student and co-worker of Tycho Brahe. We've discussed Tycho before, a larger-than-life man who worked for the Danish king and liked to party. He enjoyed his life. He enjoyed living as this very big person, and so in some ways it was quite difficult to deal with. And this often leads Kepler and Tycho into conflict. Tycho was, however, a very well-established astronomer. Tycho's nova, a huge supernova which appeared in the sky during his tenure as astronomer royal to the Danish king in the 1500s, showed that the stars were not unchanging, that stars could change, that things could appear and disappear. The Ptolemaic system of the perfect unchanging universe and the perfect stars was starting to fade, and our people's observations were starting to show that this was not true. The other thing that happened over this period was the Great Comet of 1577. This enormous comet showed, as it moved across the sky, that things could change in the sky. The heavens were, again, shown to be imperfect. And this is an event which actually influenced the young Johann Kepler. Kepler himself, as a child, was taken by his aunt and his mother to see this particular comet in the sky. And here are the constellations shown here in the sky, and here's the enormous comet in a very florid woodcut depiction here from literally 1577. And here are astronomers of the day, people with lanterns so that they can see where they're going in the dark, which probably didn't help night adaptation. But here is an astronomer making notes and sketches of the actual comet in the sky, and as you can see, here's his sketch accurately depicting this particularly inaccurate comet that's shown in this artwork. You can see the period from the dress of these people and the fact they're carrying swords. And comets, as we'll discuss at a later date, were often portents of doom before this, rather than being things to be scientifically studied and to be seen as a wonder of the universe, were often seen astrologically as being bearers of bad news, harbingers of doom. But as times were changing, these superstitions were ending, and the young Kepler was fascinated by this comet. So this is Johann Kepler. This is the man who sorted out the orbits of the planets. He was, as I said, becomes a colleague of Tycho Brahe. He made star atlases, he studied lunar and planetary motion, he looked at eclipses. He was also involved in looking at optics and studies of human anatomy. He also wrote extensively and theorized travel to different planets and thought about what the stars would look like from those different locations. So what we're going to discuss here, though, is specifically Kepler's contribution to the orbital nature of the planets and Kepler's laws. Now, Kepler was an interesting personality in his own right. He had smallpox as a child, which damaged his vision and damaged his hands, which meant he was actually working at quite a disadvantage sometimes, but was still capable of constructing incredible models of the solar system and making wonderful observations. Kepler needed access to incredibly detailed observations of the planet Mars in order to look at these orbits that he was so interested in. And what we're really talking about here by the observations of Mars are the movement of the dot in the sky that is Mars, that retrograde motion as Mars moves around in its orbit and Earth moves around in its orbit and the planet appears to go backward. And this is where Kepler was particularly interested in Mars because of its extreme retrograde motion. And he calculated the orbit of Mars very accurately. And after doing this, looked at the data for the other planets. So Tycho, this difficult personality, made the most accurate measurements of the planetary positions, down to 1 arc minute, which, without telescopes, was incredibly good. And here he is, Tycho, sitting in his observatory, and you can see this is another great depiction of an observatory. Here's a clock with a servant holding on to a candle, looking at this clock, Tycho pointing to the stars above, and a scribe here writing down his discoveries. As you can see, his dog is here at his feet. He has other people back here working in laboratories inside of his observatory with spheres and books. And you can see armillary spheres and sighting equipment to look at the positions of the stars. But Tycho made these observations and held on to these observations very tightly. He was always scared that someone was going to steal his observations and take his job. So he hired Kepler to analyze Mars or the data, I should say, of his Mars observations and solve the problem of planetary motion. Tycho wouldn't release his data, his proprietary treasured data, or allow any copies to be made, and he would only allow Kepler to see this data at a few hours during the day. And this would often slow Kepler down and hinder his scientific efforts. Tycho and Kepler had a very fractious relationship because of this, and did not get along at all, and fought on numerous occasions, some of these actually going as far as being documented when Kepler has actually resigned his position at least once during his time with Tycho. So this relationship was far from good, and Kepler was working under very difficult circumstances. Additionally, Kepler had some other personal problems. During his time of being the imperial mathematician and astrologer even, I should say, his mother was actually tried for witchcraft, of which she was actually on trial for 6 years, being placed in a particularly damp cell and chained to the floor so she could not move at some points during the trial. She was one of 15 women who were actually tried during these witch trials, many of them executed. And as you can see from this particular diagram, this here is Katharina Kepler, Johann Kepler's mother, and she's been shown a particularly vicious device of torture here. So her peril was very, very real, and Kepler was attempting to get her out of jail and was actually working hard to rescue his mother. Of course, the allegations against Katharina were quite false. She was actually a local healer, and an old woman and a local girl said that she had actually paralyzed them, and she claimed that she could turn herself into a cat and that she killed a lot of livestock. So we're thinking that the evidence against Katerina was probably inaccurate, but it was still something that Kepler had to deal with during his work as an astronomer. Kepler eventually rescued his mother from the witch trials, and she continued to live a relatively long life. However, she was seriously affected by her experiences and was actually physically disabled for much of her life due to this occurrence and due to her treatment while she was in jail. Kepler continued after this and during in his studies of the solar system. And remember, we're talking about a man here who had damaged hands and poor vision and managed to make these wonderful sculptures out of wood showing the solar system and all of its various layers of complexity. He was also into music, and Kepler actually took the orbits of the planets and took their mathematical relations and turned them into musical notes. And the idea was here that you could actually play the solar system. So the music was generated as the planets moved about the sun, and the mathematical motions of the planets could be played and listened to in the hope that some pattern could actually be discerned from this music. So Kepler was literally a polymath. He was involved in many, many different fields of study. So, in terms of Kepler's laws initially, once he came out with them, were not well received once authored. He invented this field of celestial physics. He was bringing physics, some description of the physical world, into astronomy, the perfect study of the heavens. And this was not well received. How dare he bring something dirty and something so mechanical as physics into the perfect sphere of the heavens and discuss the motions of the stars and planets? But Kepler ultimately was proven right. So he was criticized heavily. For his work, Kepler actually has a crater named on the moon for him, and here is Kepler's crater right here. So Kepler's most important contribution to science may be his laws of planetary motion. He published the first and second laws in Astronomy Nova in 1609. Now you can see there's a 10-year gap here before he publishes what he calls his third law in Harmonices Mundi in 1619. And he used these laws to accurately calculate the orbit of the planets. So the first and second law are more just observations of the geometry. The third law is actually a very useful mathematical relationship that took him a long time to come up with, or at least to publish, with all of his various tribulations occurring. So Kepler's first law showed that planets moved in elliptical orbits. Now this was very, very significant. As we said when we discussed heliocentrism, there were a few problems. When the heliocentric model first came into use, it did not completely predict the positions of the planets as accurately as the geocentric model, and a lot of people saw this as evidence that the heliocentric model was wrong. It turns out that the actual scientific nature, the actual reason for this, cannot be explained until Newton comes along 150 years later with a theory of universal gravitation. Consequently, Kepler could observe the effect of an elliptical orbit, but could not really discuss why this happens, but he did see the effect. And here's what was going on. In the original heliocentric model, as laid down by Copernicus in his work, the orbits of the planets, with the sun at the center, were perfect circles. It turns out that the orbits of the planets are not quite perfect. Some of them are close to circular, such as the Earth's rather ordered orbit, but still it's not perfectly circular. And that means that the planets moved in elliptical orbits. There is no planet that moves in an orbit as elliptical as this, but I wanted to contrast an ellipse versus a circle. In an ellipse, the circle is essentially squashed in one axis. If we do that, we make a long axis here, called the major axis, and a shorter axis here, referred to as the minor axis. What we then have is what we call two focus points. So rather than having a fixed radius from the center of the circle, we have these two focus points from which we can define our distances. Now, as you can see, if the Sun was at this focus 1 point and the planets were moving around the Sun, that means they would be closer to the Sun here and further from the Sun over here. So the distance of a planet could vary from the Sun just as it moves in its orbit. Now, we're not going too deeply into the mathematics of an ellipse, but the eccentricity, as it's referred to, is how far from being perfectly circular is your shape. So a circle will have an eccentricity of about 0. And a moderate ellipse will have a progressively larger eccentricity until you start getting to eccentricities of about 1, which are incredibly flattened ellipses. Most planets have relatively small ellipses, other than such things as Pluto, and a little bit in terms of Mercury. Comets tend to be on highly eccentric orbits. So when we say highly eccentric, we're really saying very elliptical. If it's not very eccentric, it's a very circular orbit. So what did this really mean? And we don't really need to analyze all of these complicated lines here. It meant for an ellipse that rather than having a radius, a distance from the center of the circle where the Sun would be to the planet, you have these two focus points. The Sun, represented by this yellow circle, is here at focus 1. And as you can see, as the planet would move around in its orbit now, it would actually get closer to, at this point in the ellipse, and further away from the Sun. This resulted in two terms. One of these would be perihelion, and aphelion. Perihelion is when the planet is closest to the Sun. Aphelion is when the planet is furthest away from the Sun. So depending where a planet is in its orbit, its distance from the Sun can vary. Now this is a very elliptical case. Not many planets are like this. But you can see this for contrast: close approach, furthest approach. And we have a long axis and a short axis to contend with. So in terms of Kepler's first law that he laid down, he called this the law of ellipses, and said the orbit of each planet is an ellipse with the Sun at one focus. The other focus is located in empty space. And that meant that the distance from the Sun to the planet varied as the planet moved in its orbit. Now, if we take the case of Mars, which actually has quite an elliptical orbit, this means that it can get 19%, that's quite a lot, almost 20% closer to the Sun during its perihelion than it does at its aphelion. Now, when we discussed the seasons on the Earth, we said that when a planet was tilted away from the Sun, well, when a hemisphere of a planet was tilted away from the Sun was when we had winter. And when it was tilted towards the Sun was when we had summer. I also said that Earth's orbit was quite circular, so it didn't really affect the seasons on the Earth. At 19%, not only is Mars experiencing an axial tilt very similar to the Earth and seeing seasons change because of its axial tilt and its rotation, but we're also seeing a change in the amount of radiation Mars will receive based on its distance to the Sun, which is varying quite significantly. And we can calculate these distances. So the distance to any planet at its furthest, which is its aphelion, or closest point, its perihelion, is given by these formulae. Rp is just A, that semi-major axis, 1 minus the eccentricity, or Ra is A, 1 plus E, 1 plus the eccentricity. I'll not ask you to do this calculation, but I do want to show it at least once. So if we look at Mars, and we say what's the variation of Mars's distance from the Sun? For Mars's orbit, we know its semi-major axis is 1.5237 AU, and its eccentricity is 0.0934, almost 0.1. That's quite a big eccentricity for a major planet. So at perihelion, we find that the radius, the distance from the Sun, or I should say the distance from the Sun time, which equals to its semi-major axis times its eccentricity, gives us 1.38 astronomical units. Remember, 1 astronomical unit is the distance from the Earth to the Sun. So this is the perihelion, the closest approach of Mars to the Sun. Its furthest approach, when it's furthest away, it's 1.6 AU from the Sun. That's quite a lot. That's actually a difference of about 0.23 AU. When this calculation is performed, you have to use astronomical units and years in order to look at any of our planetary systems. So here's just a quick diagram showing Earth's orbit here in the center, roughly circular, but as you can see, slightly offset. Here's a slight difference between our closest approach to the Sun and our furthest. And here's Mars's orbit. And as you can see here in January, it's actually quite close to the Sun, but over here in July, it's actually quite far away from the Sun. And quite often, when we talk about time on Mars, rather than taking the Earth calendar and sticking that on Mars, we actually talk about the area-centric longitude of the mean Sun. And what we actually mean there is what's the position of the Sun relative to Mars. And Mars ends up with its own strange calendar. We couldn't just take the Earth calendar and stick it on Mars if we lived there, because 1 Mars year equals roughly 2 Earth years. 1 Mars year is about 687 days. That's the time it takes Mars to go completely around in its orbit. So Mars has this elliptical orbit, and you can see here it's quite close to the Sun, it's quite far from the Sun. And that has a very pronounced effect on its seasons, as I said. So, as we can see here, there's a almost 25-degree axial tilt to Mars. That means if you're in the southern hemisphere, when you are nearest to the Sun, when you are at perihelion, and the southern hemisphere is projected towards the Sun, you end up with some quite warm temperatures. Likewise, when you're very far away from the Sun, and your hemisphere is projected away from the Sun, you end up with some very cold temperatures. So parts of the southern hemisphere of Mars can see temperatures up to 20 Celsius sometimes, but as low as negative hundreds of degrees Celsius. And this seriously affects the weather of this particular planet as it revolves around the Sun, based on its axial tilt and its distance. So as you can see here, there's actually a very severe regression and expansion of the polar cap of Mars. So here we are in October of 1996, and as you can see, this is the northern polar cap of Mars. The polar cap is enormous in this particular image. As it moves around in its orbit and comes closer and closer to the Sun, you can see that this polar cap has significantly reduced in terms of its surface area. This carbon dioxide ice, because this is CO2 ice, not water ice, has sublimated and turned into gas. As it moves around to March of 1997 here, you can see that all of this polar cap has disappeared and left what we call the residual polar cap. And we can see a lot of detail around the polar cap of Mars that we couldn't previously see. So this seriously affects the weather on Mars. So moving on to Kepler's second law that he came up with. And Kepler's second law is also known as the law of equal areas. And remember, Kepler here is working without the benefits of Newton's work on gravity, which would take a long time, or over nearly 200 years to come up with. So the explanations that we will give in our next lecture will make clear why these things happen. Right now, Kepler was concerned only with the effects of what he was observing. And the law of equal areas says, if he draws a line from a planet to the sun, it will sweep out equal areas in equal times. Now, that might sound a little abstract and you might wonder what that really means. But the consequence of this is when a planet is further from the sun, it moves more slowly. And when a planet is closer to the sun, it moves faster. And this is how he could now predict the positions of the planets more accurately, because it meant that where a planet was in its orbit affected how quickly it would move around the sky. So this is what the law of equal areas is really stating. Here's the sun, here's a planet at aphelion, here's a planet at perihelion. Now the planet will move in its orbit from point A to point B. When it's further from the sun, it can move from point C to point D. Now the planet at perihelion, if we look at the area of this line, this sort of pizza-shaped wedge here, it will actually carve out a short, wide area as it moves in its orbit. At its longest distance, when it's furthest from the sun, it'll carve out area 2. This is an aphelion and is a narrow, long area. These areas should be equal. So what that means by Kepler's mathematics is that at perihelion, the time taken to get from A to B is the same time to go from C to D. But the planet is covering a much shorter distance here than it is over here. So by Kepler's calculations, the planet is going much faster when it is at perihelion and much slower when it is at aphelion. And as I say, this requires Newton to come along and come up with a theory of gravity to explain why this happens and how the energy of a planet changes in its orbit. And Kepler here is really just discussing the effects on a planet in the sky and relating this to the orbit. So here's what Kepler was really saying. Here we have a simulation that shows the orbital radius of a planet and, of course, its orbital speed. So here's the distance essentially in its orbit, and here's the speed that the planet will move at. And we can change the eccentricity of our orbit. If we make it 0 here, we can hit begin, and as you can see, the orbital speed of a planet in a perfect circle will stay exactly the same anywhere on this point. If we vary it just a little bit, we should be able to see here that now the orbital radius is changing just that small amount and the orbital speed is reducing at this point. It's actually reducing the whole time it's getting further away from the sun and increasing as it approaches the sun. Let's increase the eccentricity even more. So now we can actually look at the radius and speed. Here we are at aphelion, the furthest point from the sun, and as you can see the orbital speed is low. As the planet approaches the sun now, it starts to speed up. As it goes further out, it slows down. So there's a definite relationship between the speed of a planet in its orbit and the radius of the orbit. The further away from the sun, the slower the planet goes. The closer to the sun, the faster the planet goes. And this is to do with converting gravitational energy to kinetic energy. But Kepler didn't know this. He was simply explaining the effects. Now, Looking at this particular relationship, we should be able to plot the average orbital speed of the planets versus their distance from the Sun. Now remember, Kepler didn't know about planets outside of the orbit of Saturn, and by plotting out these planets, he could actually look at these speeds. And he determined that the planets closest to the Sun, such as Mercury, Venus and the Earth, were all moving much more quickly than the planets further from the Sun. This graph shows the average distance from the Sun in astronomical units and the average orbital speed here in kilometers per second. So these are very high speeds. These are thousands of meters per second. That's how quickly the Earth is moving. So the Earth is moving at about 30 meters per second here at 1 astronomical unit. Mercury, so close to the Sun, is moving towards 50 meters a second. Venus at 40, Mars here somewhere around 25-ish, and Jupiter around 15, Saturn at around 10. And the outer planets are moving even more slowly, meaning it takes many, many Earth years in order to make one journey around the Sun, to make one orbit. And in terms of the eccentricity of the orbits, as I've said before, most of the planets are relatively well behaved. Earth is quite circular. Venus is quite a circular orbit also. Mercury is in a very high gravitational field, right here tightly bound by the Sun, and tends to misbehave a little bit compared to the others. Most of the other planets have relatively nice circular orbits until we get out to something like Pluto, which has a very, very pronounced eccentricity. The most eccentric orbits that we know of belong to such things as asteroids or comets, and here is Halley's comet here on its incredibly eccentric, highly elliptical orbit that brings it back every 70 years or so. So in 2024, Comet Halley is actually at one of its furthest points in its orbit. And there's the eccentricity of the various orbits. Mercury at 0.2, Venus and Earth at about 0.06, 0.01, Mars with almost 0.1, not very well behaved, Jupiter at about 0.04, and Saturn about along with it. So these gas giants actually have quite circular orbits, and then Pluto out on the edge with the most elliptical orbit. And one of the part of the justification as to why Pluto was thrown out of the Planet Club. So looking at these, we can see that there are different types of planetary orbit, different extremities to our ellipses, and so we can say that planets can take a number of different forms. They can be circular, elliptical, or what we refer to as parabolic or hyperbolic in terms of the function of their orbit. And this was often shown, especially in Kepler's day, as what were referred to as conic sections. And this means if we take a cone and we cut through a cone perfectly. So here's our cone. If we cut through it laterally this way, it will make a perfect circle and give us something with an ellipticity, an eccentricity even, of 0. If we cut through this cone at a higher angle, it'll give us an elongated circle, an ellipse. And this ellipse can range from either 0 to about 0.99999, just before 1. And that means anything that is circular or elliptical has what we call a closed orbit. If we put a planet on anywhere on this track, it'll go round and round on this closed orbit and repeat its motion indefinitely. If we cut through our circle at our cone at a very high angle, we will end up with what we call a parabola. And this is something with an eccentricity of 1 or above. And as you can see, this is no longer a closed orbit. So between 0.6 and 1, you still have your closed ellipse, but getting progressively more severe. But over 1, once we exceed 1, we have this parabola. And this means anything that's in an orbit that's parabolic will not repeat its cycle. This is the kind of thing that will come into orbit with very high energy and then be flung off into space. Such things as the Voyager probes that we discussed previously would have been on parabolic, or, in the more extreme case, if we cut through our circle, through our cone even higher, a hyperbolic orbit. And here we have eccentricities of about 1.4. So these cases are cases where the orbit is not closed, where it's what's referred to as an open orbit, where our vehicle or planetary body or whatever is under gravitational attraction will fly off into space. So circles and ellipses form our closed orbits, where a body will keep returning and going around in its orbit. A parabolic trajectory can sometimes be closed, but is nearly always open, because it's on that cusp, that E equals 1, but most parabolic orbits tend to be open. And then we have a hyperbolic trajectory, in which an object that was orbiting the Sun on a hyperbolic trajectory will nearly always, or will always, be flung out of the solar system, unless it hits an object before it makes it out of the system, which is incredibly unlikely. And when we talk about parabolic orbits, this is the kind of thing that was done in early days of the space program. So in the early space program, Russia launched its spacecraft into space, launched satellites such as Sputnik and men such as Yuri Gagarin into space, and put them into orbit. That meant that they were in elliptical orbits and went round and round on a repeating cycle all the way around the Earth. The United States, on the other hand, wanted to catch up in what was referred to as the space race, but the rockets available to the USA were nowhere near as powerful as those available to the Russians, and this was extremely embarrassing, technologically and politically. As such, NASA was ordered to put people into space in order to catch up with the Russians. In fact, that was the reason NASA was founded. And of course, they had to use the rockets at their disposal. These rockets, not capable of putting things into orbit, used a parabolic trajectory. A person was put on top of this rocket and they were fired up into space. In fact, Alan Shepard, the first American in space, was in space for about 15 minutes, and then the spacecraft would return to the Earth in this parabolic trajectory. So not an orbit, just going up, flying into space and landing again. Very much like throwing a rock, a very powerful hydrogen-fueled rock. So in terms of our closed circular orbit, here actually played by Sputnik in its orbit, your spacecraft will just go round and round and round and round and round. In an open hyperbolic orbit, a vehicle or natural body will come in this case, again played by a spacecraft. Sputnik here will come into orbit of the Earth and speed off into space, not repeating its cycle, but never to be seen again. So that's the first of Kepler's two laws, and their effects and their implications. Let's finish off Kepler's laws here with Kepler's third law. And remember, this is the one that took Kepler 10 more years to come up with. And it's the only one that we can really apply a true calculation, or formula, I should say, to. And Kepler's third law makes this statement, that p squared is equal to a cubed. Now, p here is the period, or the time it takes a planet to go around once in its orbit. A is the semi-major axis, the long axis of the orbit. So p squared is equal to a cubed. If we cube something, we're essentially taking it to the power of 3. If we square something, we're taking it to the power of 2. And that's the relationship. So Kepler's third law really makes a statement. The square of the orbital period of a planet is directly proportional to the cube of its average distance from the Sun. Or p squared equals a cubed. There should be a constant in here, k, which makes this formula work perfectly and refines it even further. However, this needed Newtonian gravity. This needed someone like Newton to come along and come up with a theory of gravitation in order to insert that constant and make it even more accurate. And as we said, it took Kepler 10 years to develop the third law. It takes another 150 years to develop gravitation to complete this particular quest to explain the orbits of the planets. So, P here, when we're using this equation, P here it should be in years, and A, the semi-major axis of the planet, should be done in astronomical units, where Earth is equal 1, based on the orbit of the Earth. So if we plot P squared equals A cubed for every single planet in the solar system, we get this really nice straight line. And this is proof that Kepler's laws actually work. So you can see by the scale of this graph, this is the average distance from the Sun cubed, and this is the period squared. So Jupiter is out here approaching about 150, Saturn's out here at about 800, 900. So that means that Mercury, Venus, Earth and Mars, if we're looking at the square of the years and the cube of the distance, fit into this tiny little square down here. And this particular diagram blows them up for clarity. But we do end up with this beautifully straight line, showing that P squared equals A cubed works. So if we take Kepler's third law and we say that P squared is equal to A cubed, where A is equal to 4 astronomical units. So we've discovered some hitherto unknown planet at about 4 AU. What is the orbital period of the planet? Well, P then will be equal to a square root of A cubed. So it'll be equal to the root of 64, which will be 8. So the orbital period of this body will be about 8 years. And this calculation works for any orbiting body, any planet, any moon, any satellite. And it doesn't just work for the Sun. Here we've used the Sun as the example because we were talking about the development of the model of the solar system. This also works for the Earth. If we put a spacecraft in orbit around the Earth, the only thing that changes is the terminology, in that the closest approach to the Earth we refer to as perigee, and the furthest approach we call the apogee. This also works with Mars, peri-air and apo-air, or any other body of significant mass of which we can go into orbit around. Jupiter, even, being the biggest body in the solar system other than the Sun, where we have apogee and perigee. So this will apply to any gravitational source, as long as you're using astronomical units and P in years. I'm not going to ask you to perform this calculation, but this is how it was done. And in our next lecture, we will talk about how people like Newton came along and changed this rule once again and truly revolutionized the way we view the solar system by adding gravity to these observations and adding gravity to the work of Kepler. So there's a summary of Kepler's laws. Its first law states that planets move in elliptical orbits, which was extremely controversial and showed that the heavens were not perfect, and actually gave proof of this when he came out with the third law of P squared equals A cubed. But the effect of the first law is that the distance from the Sun to a planet varies as the planet moves in its orbit. The second law, if we draw a line from the planet to the Sun, sweeps out equal areas in equal times. Its effect is when a planet is further from the Sun, it moves more slowly. When it's closer, it moves faster. So Kepler's law is really a geometrical trick, a geometrical method of figuring out the speed of a planet in its orbit. What we really care about is these effects, how the distance from the Sun to a planet varies, and how the speed of a planet varies as it's closer and further from the Sun. And of course, these two tie into law 3. The square of the orbital period of a planet is directly proportional to the cube of its average distance from the Sun, or P squared equals A cubed, giving astronomers for the first time, a formula to which they could plug in distances and they could plug in times and they could actually characterize the orbits of the planets. We'll continue this discussion next time, where we'll add Newtonian gravity and complete our model of the solar system.